Hello class, in this lecture I want to somehow discuss the turbine calculation, but now we want to take a complete look at this steam power plant calculations. So this is a little bit more than turbine calculation itself, because we know that if I'm going to have a steam power plant, I'm going to have the following units for the 4 units. This is a boiler. This is a turbine. And I'm going to have this as a condenser. And I'm going to need a pump. To finish the whole process. The boiler, I'm going to have this heat input from a hot reservoir. The condenser will discharge some heat to the cold. Turbine will output the useful shaft work. Pump would need some shaft work to compress the fluid. So this would be the flow. So this is the so-called steam power plant. And you probably realize that for both Catnot cycle or the Rankine cycle, we are using the same design, but of course they have their difference, and we will see that in a minute. So by looking at this, I also want to review. So now if you go from this diagram to the PV diagram, then I hope we still recall that I'm going to have the PV pressure volume diagram. Over there I'm going to have 2 temperatures from the 2 reservoirs. One is TH, one is TC, hot and cold reservoir. So the boiler would be over here. Let's say we start with this liquid A. I'm going to use a pump to move the system from A to B, and that whole process we call this as adiabatic compression, right? This is adiabatic compression in a pump. PUMP over here, this is my unit. Then moving from state B to state C, along this isothermal expansion, the volume is increasing, moving from B to C. So this is isothermal expansion, and that unit is boiler. And then moving from C to state D, then I'm having the adiabatic expansion, which is carried out in a turbine. And then D to A to the starting would be in my condenser. And of course we can identify the heat and workflow. This is the QH into the system. This is QC leaving the system. This is the shaft work of turbine out of the the system. This is the shaft work or the pump work into the system, right? And we also discussed that if I'm going to have a TS diagram to go together with that whole complete steam power plant, then I would have this. So if I'm going to convert that into a TS diagram, this is T, this is entropy, then I would have A, B, C, and D. A, B, C, and D. This is the adiabatic compression. This is the corresponding TH. This is the corresponding TC. And then this is the isothermal expansion, adiabatic expansion, isothermal compression. I'm going to have A, B to C, C to D, and D to A. Alright, so of course I'm still having this as pump, boiler, turbine, condenser. Over there. And along that process, I'm going to have SA equals SB. I'm going to have SC equals SD. So this is the isentropic process. But of course, in order to satisfy this, I have to have this as reversible. Right? And then you can see that is the typical discussion we had for this Catnot cycle. But then, as we saw in lecture 12, we also discussed that, hey, I need to make a small modification, small but important modifications. This is simply because we need to use this Rankine's idea. And the idea is basically looking at the point C and state A. So now if I have this as the modified, slightly modified TS diagram, then I'm going to have, let's try to copy this A, B, C, D over here, A, B, C, and D. It's coming from the D over here. This would be the general curve. Then we can see the two places with modifications. One is the state C. So over there we try to move this to the C prime. Over here we at least would move this to this A prime over there. Let me try to modify A. This is my A. This is B. C is here. C prime is over there. This is A. Okay, so for the modification of state C, this is we are going to have over here at C, we are going to have a mixture of high temperature vapor and liquid. Okay, we are not very happy with this because this content of liquid would be very reactive and I can easily destroy my turbine. So we try to move state C to C prime. The whole purpose is to reduce the amount of high temperature liquid. This is the purpose of making that change. Then for this state A at this A, we are going to have a mixture of low temperature vapor and liquid. We are not very happy to use this as the inlet to the pump because the efficiency of compressing vapor is not that nice. So we try to at least get rid of as much vapor as possible. So move from state A to A prime. We are trying to reduce the amount of low temperature vapor. So you see we are trying to get rid of vapor over here, trying to get rid of some liquid over there. So this is the key concept of Rankine cycle. Now if you try to stick with this actual state while we are doing the calculation, then we are having the actual A, which is A prime, B, C prime, and D. So that would be the curve we are going to have. D would be somehow over there. So now the question is about the D. So you can see that for state D, we could do as I have on this plot, or I could do as this, or I could do as that. Okay, so there is a question about the D. For this for state D, we could have a superheated steam, right? We could have a saturated steam, or we sometimes call this as a dry steam. So the difference would be for the superheated, of course, this is vapor. Okay. For the saturated, this is vapor plus liquid. for the dry steam, that is a little bit complicated to convince you, but if you look at the tie line, over here, especially for that point, we are going to say the real physical definition is vapor plus liquid, but over there we are going to have the last drop of liquid, and we assume the amount is really we are able to neglect that, so we would consider this is almost a pure vapor phase at that condition. Alright, so those would be the understandings looking at the Rankine diagram. And then I hope you recall the discussions we had about the two important processes. This is pump, this is the turbine. So now you see that when we were talking about the calculations, let me say this is 1, let's call this as 1, let's call this as 2, calculations of pump and turbine. You probably would ask, hey, what about the calculation of boiler and condenser? Well, I can tell you that the calculation of boiler or condenser, which is sometimes a heat exchanger, we actually had that in the first midterm, which is P3 of midterm 1 of our week there, right? So now for the calculation of pump and turbine, then as we discussed in class, if we are looking at this HS diagram, this is the two pressure. This is P1, this is P2. Okay, so P1 very often, this is initial is coming from what? This is, let's say this is a HS diagram for turbine. Now if you take a look at this turbine inlet over there, so this is the turbine inlet, so very likely we are going to have this as the superheated steam. And by superheated steam, I hope you realize that, hey, according to the Gibbs phase law, F is number of component, C minus pi plus 1 would be, this is about water. I'm going to have the 1 vapor phase, so then I need 2 conditions. So I need to know T1, which is really the case of the problem statement or in our real life. Then for P2 is a little bit complicated, that as we discussed, which is corresponding to the state D, but quite often we are going to deal with saturated steam. By saturated, we know this is a vapor plus liquid. So here if I do the calculation, F is still C minus pi plus 2 is 1 minus 2 plus 2, which is 1. So that implies if I know P2, then I should be able to know T2. Okay, this is the first information. The second information is along this. This might be quite useful. This is along this curve over there. P2 path or curve. I have P2 and T2 known and fixed. What I mean by this is, if you take a look at this, for example, this is state A, I have state B, A and B, they are composed of the same vapor at T2 P2 and liquid T2 P2. Okay, they are composed of the same vapor and liquid, but having different ratio of vapor to liquid. This is the key. So you would see that in a minute in the example. So very often, in order to understand this mixture of vapor and liquid, we define the X value. And by the way, I had a mistake in the previous video of turbine calculation. So this X is defined as indeed as vapor of the steam, and the steam is a mixture, so this is defined as vapor over vapor plus liquid. Alright, so from that you can see, if I'm going to have the enthalpy of condition A or state A, then HA is from the H liquid coming out of this T2 P2, right? This would be the total. Let's say this is the total, plus H of the vapor at the same T2 and P2, and also total value. Alright, so now if I do this as one more of this saturated steam, then I'm going to have this modified as HA is HL of T2 P2 plus X times HV T2 P2 minus H liquid T2 P2. So we can double check if this equation is making sense or not. by looking at the two extremes. One is, for example, let's check. If x goes 0, meaning I have no vapor at all, then this is a pure liquid. And if I'm gonna use this x equals 0 for this equation in the red box, then I would have HA. Yes, x goes 0, then the whole term would be HL T2 P2. It is indeed the pure liquid. If x goes 1, which means by the definition of the x, which means I'm going to have pure vapor, then I can have HA. Yes, x now equals 1, which is HL T2 P2 plus HV T2 P2 minus HL T2 P2, which is indeed HV T2 P2. So that check tells us this is a good equation according to the definition. And of course we can have the other quite useful equation, which is the entropy calculation. SA. Yes, S of liquid at that temperature pressure condition plus X times S entropy of the vapor at that temperature pressure condition minus S of the liquid T2 P2. Okay, that is one other very useful calculation if you know this is a saturated steam and you know the ratio of vapor to liquid. So coming back to the diagram itself, we understand that we need to apply. I'm going to have the diagram again repeated. This is H and S diagram. This is H, this is S. So I know now this is P1 and T1 I have to know, and this is P2 and T2 is known from P1, no P2. I have this initial 1, then I'm going to carry out this isentropic process for this we call in the lecture. This is 2 prime, and that is the actual 2. So you can see that 2 and 2 prime, they are having the same vapor and liquid at the T2 P2, but their ratio, vapor liquid ratio, should be different. Okay, so why this is important to identify this isentropic? Isentropic meaning delta S is 0. That is answered by the purpose of the turbine. So this is still turbine, which is for the turbine. Let's say I'm going to have a turbine. This is my inlet of the turbine. This is my shaft work output of the turbine. This is my outlet of the turbine. So if I apply the first law of thermal, I have delta H plus half delta U square plus G delta Z is Q, the heat, plus shaft work. I want to warn you, this delta U is half U. Alright? And then we know for a turbine, really the purpose is to receive the maximum shaft work, and we typically don't allow any heat leakage. We'll try really hard to avoid heat leakage, and we don't need to worry about lifting this to the 10th floor, or we're not going to change the inlet and outlet tube diameter. So by using all those terms, would be 0. This is delta H, would be shaft work. Okay, and then according to Carnot, the maximum efficiency is coming from the reversible process. So if reversible, then we would have delta H along this isentropic would be maximum shaft work. Okay, using that understanding, we also define the efficiency, which is the delta H isentropic over delta H actual is same as shaft work actual over shaft work maximum. Or if I'm sticking with this 1, 2 and 2 prime, that would be H1 minus H2. So here H1 and H2 would be numerical values. I've figured out the sign, and I'm simply looking at the actual numerical values. This would be H1 minus H2, H1 minus H2 prime. Okay, this is the definition of turbine efficiency. So by doing this, I hope it's not too difficult for you to review and have a better understanding of the pump. It's again the HS diagram, but for the pump we are actually moving, hopefully thanks to the Rankine cycle, we are moving from this is one, no, let's call this is a pump process. So this is my isentropic process 2 prime, this is my actual process of 2. So now you can see that the pump, this is T turbine, see the pump is defined as delta H isentropic versus delta H actual. This is because that is the shaft work minimum input. This is the actual shaft work input. So the key is input. There we are interested in this as output. This is why we are defining the efficiency like that. Hope it's making sense. P is not the pressure, P is pump. T is not temperature. Let's try to modify this. T is turbine. Okay, so now you can see if I go back to this isentropic, no, to the Rankine, cycle, I'm going to have two isentropic processes. One is turbine, one is pump. Okay. Alright, so this is the general discussion of the steam power plant. But let's try to have a problem so we can have a good understanding of the procedure. Number 3 is example. And that example is coming from problem 3 of midterm 2 out of 2016, I believe. Let's try to have the problem statement. So I'm going to insert this. Let's say insert file from my job box, from the course 2018. This is our class. This is supporting video, and I have this problem statement as a screenshot. Yes, nice. Oh, try to enlarge this a little bit. Okay, that should be good enough. Oh, not this. So now let's try to read. This is a steam power plant is shown below. The turbine operates adiabatically, which makes sense. Let's say this is adiabatically with inlet steam at known temperature, known pressure. So I'm going to have this specified over here. Let me try to take a look at this correct. This is turbine, and the inlet is coming out of here. So here I'm going to have 575 and 7 MPa. I have this as a inlet, and I know this is temperature and pressure, so very likely I'm going to have a super heated steam. Okay, and with the known temperature and pressure, I should be able to figure out if this is 2, then I'm going to call this as H2 and S2. It's a pure vapor. It's a pure vapor over here. And as the problem statement says, and the exhaust steam enters the condenser at 54 degrees C with a quality of 0.96. What is that quality? The quality is, as I defined later, is a steam quality of 0 indicates 100% liquid, while a steam quality of 100 indicates 100% of vapor. Yes, maybe I should use vapor. It's more easy for us to understand. So we understand that at this stream, or at this this condition 3, I'm going to have 54 degrees C. This is saturated steam, meaning vapor plus liquid. Okay, so by using the saturated steam table, I shall be able to figure out what is the pressure. Let's call this P3. What is the pressure I should be able to get. And for the vapor, what is H3 of the vapor, and entropy 3 of that vapor, and liquid H3 of the liquid, S3 of the liquid. Okay, but I don't know their ratio. Actually, I know their ratio is provided is 0.96 milli vapor, 4% of liquid. Okay. What else? What else I have? Then I also have this is saturated liquid. Where, okay. I also have saturated liquid leaves the condenser. Saturated liquid leaves the condenser and is pumped to the boiler. So here I'm going to have this as saturated liquid water leaves the condenser and is pumped to the boiler. So now let's take a look at that saturated. So if I know this is saturated, then I only need to know one condition, temperature. What is that, T4? Okay. And if I know the temperature of this saturated liquid, I probably have to explain that if this is a saturated liquid, that is more like the it's like the corresponding to the dry vapor. It's actually 100% of the liquid. At that condition. So I will use the corresponding H4 of the liquid, and I would need S4 of the liquid over there. And then there's a problem about this temperature 4. So now if you think about this boiler and condenser, so we are going to have a phase change in both the boiler and the condenser. While we are having the phase change, the temperature and the pressure will not change. So there we have to understand this, and then we need to figure out this is also 50 degrees C. This is the first challenge over there. Now let's keep reading the problem statement. Now it says neglect pump work and kinetic and potential energy change. So now there's for the pump over here, there's a shaft work of pump is 0. The delta U change would be 0. G delta Z would be 0 as well. Okay, so that would imply, if I'm going to set up the equation only for the pump process from 4 to 1, for the pump process, first law of thermal is again delta H plus half delta U square plus G delta Z would be Q plus shaft work. Okay, so I'm going to have this as 0, this as 0, this is also 0. What about Q? Well, this is a pump, right? Q for pump, Q for pump, for turbine. They are 0. That implies we are going to have delta H is 0 for this problem, for the pump. Unit. Or we can have quite nice, quite useful equation, which is H1 is H4, because this is 4, this is 1. Okay, that is everything I could have after reading the problem. Let's take a look at what the question is. The hint is pay close attention to each unit to understand its inlet and outlet. This was what we tried to do. And what process model you may use, such as isotherm, adiabatic, isentropic, so on. And use the provided steam table to determine, one is what is the turbine efficiency. Okay, then we need to calculate the turbine unit. 2 is what is the thermal efficiency of the cycle. So now the thermal efficiency of the whole cycle is this is QH. This is the paid cost we do purposely. And then would be the useful work. Generally is defined as the shaft work difference between turbine and pump. Now, since we don't have any pump shaft work, so this is simply the shaft work of the turbine over the QH. So we also need to calculate what is the boiler, what would be QH. So here, for example, if we take a look at this QH, I have some understanding of the H1. For example, this is H1 from the H4 calculation, and H4 we probably need to use the steam table to figure it out, and then I know what is H2. So for the boiler, if we apply the first law of thermal, let's say for the boiler process, it's again by using the first law of thermal, Q plus shaft work over there. So for the boiler, no shaft work, right? No internal energy, no kinetic energy, no potential energy. So that would give us that QH simply delta H, right? What is delta H? Delta H is H2 minus H1. Okay. So now I feel like as long as we are able to read the steam table for all those conditions, and we perform the calculation of the turbine, part B shall be straightforward. Okay, so let's try to solve that. Then I'm going to refer you to the actual solution we did, and I hope then you can understand what I was doing in the solution. So we started with the strain tool. So for strain tool, let's call this as strain tool. So now we have this superheated, and I know the temperature, and I know the pressure. Use steam table, but I don't have that exact temperature condition. So I was picking up the two condition. Use 7 MPa, but the two different known temperature condition. One is 550, one is 600. So you can see that this is my 575. This is 25 degrees C lower. This is known condition, 25 degrees C lower. This is 25 degrees C higher, 600 degrees C. So by picking up that 2 points, I can simply take their averaged values as my superheated steam. This is why H2 would be half of the known 2 enthalpy values, which is kilojoule per kilogram. Pay close attention to the units with steam table, and that too are explained simply because the 2 points are 25 degrees C from the interested condition. Otherwise you have to use level rule to figure out the calculation, and I can receive this entropy of the interested steam similarly. This is 7.0155. Pay attention to the unit as well, kilojoule per kilogram per Kelvin. So let's try to figure out the entropy and enthalpy for all the strain. So now strain 3 is 50 degrees C. This is a saturated or a mixture of liquid and vapor, and I know their ratio would be X would be 0.96. So using the steam table, liquid, their H3L would be kilojoule per kilogram. S3 of the liquid would be kilojoule per kilogram Kelvin. Vapor, H3 of the vapor should be much larger than the corresponding liquid. This is why vapor is always useful for any heat supply. 8.0091, more crazy, so of course having a larger entropy value than the corresponding liquid. So we know what is the ratio of that two, then we are able to calculate the H3 would be H3 of the liquid plus X times H3 of the vapor minus H3 of the liquid. So I'm not going to, let me try to put down those numbers for you. minus 225 for 8. This is I cannot do the calculation that fast, simply because I'm actually reading the solution. So the key is to go over the whole procedure and trying to explain so you can understand the solution easily. Then of course very similarly we can figure out what is the entropy. Okay, S3. In my solution I did not have that because we were actually not using this entropy value entropy calculation. But no matter how you are welcome to solve. This is still S3 vapor minus S3 of liquid, and then you just use those values over there to finish the calculation. Now for that turbine, remember that this is we call this as 3. Let me see, 3. This is coming from this 2 coming out of the actual 3 according to the diagram. So 2 is my inlet, 3 is my outlet. So and then for the turbine I need to figure out this isentropic process, right? This is 3 prime. Okay. So now according to the isentropic process, I know S3 prime shall be exactly the same as S2, and S2 is what? S2 is over here is 7.0155 kilojoule per kilogram per Kelvin. Okay. So if that is the case, then I also know this isentropic process for that condition. This S3 prime is coming from this S3 of liquid plus, now this is X prime. Okay, it's not the grade of 0.96, but it's a different one, simply because this is known 0.9, but that we need to figure out in order to calculate H3 prime. So this is X prime, S3 of the vapor minus S3 of the liquid. So by doing this, we are going to have 7.0155. Yes, the liquid is 0.7543 plus X prime. This is a vapor 8.0091 minus. So we understand X prime is. So you see that it's different. Now we understand this value is different from this one. Okay. So now if we know this, then H3 prime over here is a mixture of vapor and liquid, and now we know the ratio, and they are still the same temperature and temperature. It's say P3 and T3. Okay. So they are on the same temperature and pressure curve. The only difference is two mixtures. They are having different ratios of vapor and liquid. So this is why H3 prime is H3, still the same H3 liquid. But now I'm going to use this new calculated ratio for that condition. This is H3 for the vapor minus H3 for the liquid. I can finish the calculation by using those numbers. Now this is the actual ratio of the imaginary isentropic process. minus, okay, this is kilojoule per kilogram. Alright, so now we can use that efficiency definition. So efficiency calculation is required, and I know this is from delta H over delta H isentropic. This is H3. The actual is H3 minus H2 over isentropic would be H3 prime minus H2. Right. And I know all those values. H3 is from the calculation over here. Now H3, H2 is from the reading. H3 prime we just finished calculating. So that is we have the efficiency is. That is the efficiency of the turbine. Okay. Then what would be the shaft work? The shaft work we need to calculate, because I'm going to use that to calculate my overall efficiency of the steam power plant. So the shaft work of the turbine is indeed delta H, actual delta, which is H3 minus H2, which is that will give us a negative kilojoule per kilogram. Negative making sense because this is the work done by the system to the surrounding. Should be a negative value. But of course, if you report this as the positive value with the same numerical, that should be exactly fine. Then for the boiler, as we discussed, for the boiler, if we go to the top, the boiler is basically having this as my simplified first law of thermal for the boiler unit. So this is for the boiler. It is QH is simply H2 minus H1, and I have the H2 value read from the table, and H1 is basically H4, and H4 I can read it from the steam table as well. So this is why for this part is H1 H2 minus H2 minus H1, which is H2 minus H4. Okay, H2 we figured out, H4 we again use that steam table, so I can figure out this is minus 205. This would be kilojoule per kilogram. So now you use this this definition for the whole cycle. Yes, basically shaft work versus QH. So this is why we could finish the calculation by definition. Alright, that is a very nice problem, and that it requires the reading. Let's go back to the diagram. It requires the reading of all sorts of diagram, all sorts of units, all sorts of tables, and we probably need to understand this as again, I want to repeat, we are going to have a saturated steam, we are going to have a superheated steam, we are going to have dry steam. Sometimes we have the saturated liquid. So those would be having slightly different meanings. Sometimes we would have this as wet stream. This is basically vapor plus liquid. Superheated is vapor itself. Dry steam is vapor itself. Saturated liquid is liquid itself. Okay, so by the diagram, this is A, this is B, this is C, this is D, and of course you could have this E. See again, liquid. So now we have this saturated is D. Okay, superheated more or less is A. Try to make it consistent. Lowercase a, b, c, d, e. Superheated would be A. Dry steam is over there for the vapor, would be B. Saturated liquid is the liquid itself, but at the saturation line is C. This would be D. Alright, I think that's enough for this lecture, and I'll see you guys next Monday.